In this video, we're going to define the quantity variance, and we'll look at some properties, examples, and then we'll look at the variance for some of our commonly used discrete distributions. All right, so where does this fit in on what we've been doing so far with random variables? We started by coming up with the definition for the distribution of a random variable. And we've talked about visualizing that or writing it as a table, or sometimes we're able to write it as a closed form function. In addition to the definition, we often have properties that help us summarize things about the random variable. Two common properties are the expectation, or the expected value, and the variance. So last time we looked at the expectation, which was basically capturing the average value of your random variable. And today we're going to look at the spread, which is we're going to quantify via the variance. I want to point out with both of these properties that these are summaries, they're numbers, they're not random. Once I give you a random variable, a distribution, there will be one exact variance, one exact expected value for that given random variable. All right, so why might we care about quantifying variance? Let's look at some data about weather on the East Coast versus the West Coast. So Palo Alto is on the West Coast, and we're looking at just some expected values of the daily highs over a given time period, and then the expected value of the daily lows in this area. And we're going to do the same thing with Washington, D.C. And we can see, in general, these values look pretty close. And so I might be tempted to say, oh, I bet the weather's pretty similar in both of these two places. Not so fast, and if you know anything about the Bay Area versus Washington, D.C., their weather is not that similar, because what we're not capturing when we just look at their average is their variability or their spread. So Northern California has smaller variability. It's usually pretty nice and pretty warm. Washington, D.C. experiences all the seasons and definitely has a much larger spread. And so now we want to come up with a mathematical way to quantify this. I want some measurement that I can say is smaller for this distribution than for this one, even though their expected values are basically the same. Again, what we're showing here is a density or a normalized histogram of real data. And so we can think of these as approximations of the actual probability mass function for whatever our underlying distribution of weather is. Okay, so how are we going to quantify this variability? One way we could do this is to say, because I want the number to be smaller for this distribution than this one. So I could say, well, let's just take the range, the biggest value minus the smallest value. Okay, well, that would give me a smaller number here than it would here. But if I also had a distribution, let's get a color here to see, that looked just like this. I'm trying to make it look just like a uniform distribution with the same range like this. I wouldn't be able to, they'd have the same range and probably the same expected value, but they definitely don't look the same. And so I want that variability quantity to actually give me some information about how this varies around the mean. Is it uniformly spread out from the mean? Is it clustered around the mean? What does it look like? And so one thing I could do is just say, well, let's see how far away the data is on average from the mean. To think through this in the next example or in the next page, what I want you to imagine is I have a distribution. I have some type of, for example, probability table. I'm going to just take like the basic one that we've done here. Like I have a couple values, maybe 2, 3, 4, and 5. I'm going to just guesstimate what these might be. So maybe this is 0.1. Maybe this is 0.3. Maybe this is 0.6, 7, 8, 9. There we already added up to more than one. So you better back up, lady. How about 0.05, 0.1, 0.2? I'm just gonna eyeball this. Okay, 3, 4, 5, 6.5, and then let's say, okay. So together these are supposed to add up to. It's not at all the distribution that we have here. All right, back up. Let's not do this. Back up. We're gonna edit this. So to be able to visualize this better, on the next slide, I'm going to imagine that we take a list of data points and we basically distribute that data according to a given distribution. So if 10% of the data has this value and 20% has this value, I'm going to create a list that follows this distribution of the data. All right. Why am I doing that? So if we think of it that way, then the expected value of x of your actual random variable would be equal to the mean of your data points. And we did this example like this in a previous lesson, but again, I'm basically creating a set of data points that say has this distribution. Then I could say, let's calculate the average deviation from the mean. So let's take each of the data points and see how far away, or see their difference. And I take that minus the mean and then average it all out. But on a previous homework, you proved that no matter what distribution I start with, this will always be 0. So I'm on to something, trying to calculate this deviation from the mean, but the average deviation is always going to be 0. I'm not going to get info. And so if you're thinking, well, why not do something like an absolute value or a square here so that I don't end up getting everything to cancel out? That's the way that statisticians started thinking when they were trying to come up with the measure. And so the most common one that we're going to talk about today is actually to take the square of these values. So the average squared deviation from the mean. And another name for that is the variance. So here I have 3 different distributions where their expected value is the same for all of them. It's right here, it's 3. But the shape and spread are very different. And so let's look at how this variance quantifies that difference. The way we define it is the average squared deviation from the mean. So what do I mean by that? X is my random variable, mu is the mean. So I'm going to take the square of the difference, and then the expected value again is like an average. So this is also written, if I don't want to put mu, I could put expected value of x in here. Note, this will always be positive because I'm going to be squaring the values in here. Other names you might hear this called is the second central moment, or the square of the standard deviation, which actually leads us to the definition of standard deviation. So the issue with variance is because I have squared these deviations here, these distances, my units, well, I guess they're signed, I don't want to call them distances because some are positive or some are negative. Because I've taken these values and squared them, my units are going to be in the units of x squared, which is kind of hard to interpret, which we'll see in a minute on the next page. So the beauty of the standard deviation is it then puts it back into the units of x. So we just take the square root of the variance just to get back into our regular units. Okay, so what do I mean? So if we're going to calculate the variance for the Palo Alto or the Stanford weather, Stanford is in Palo Alto. Here's my expected value, 68. And now for each other data points in my data here, I'm going to see what is the difference, 57 to 68, and then I'm going to square it. What's the difference? Square it, difference, square it. And then I'm adding those all up and taking their average. So take this, add it all up, take the average. In this case, I'm going to get 39 degrees Fahrenheit squared, okay, which doesn't really feel like something I can interpret, but here I have 6.2 when I take the square root. And then I can come and look where that is on this plot. So this is 65, this is 70, so I'm going to basically go plus or minus 6 from here is 1 standard deviation. Let's go roughly like that. Okay. And we're going to talk a minute about what we know about what's within 1 or more standard deviations, but I can at least see it's small-ish. It's only 6 degrees. I'm going to contrast that with what happens with Washington, D.C. My variance is 248, and so when I take the square root of that, I'm getting 15 degrees. So standard deviation is square root of 248 is 15, approximately 15 degrees Fahrenheit. And then I can see a much bigger spread. So coming up like more like that for one standard deviation. And that's also helping me understand, yeah, this data is spread out more in this distribution. Okay, so why does this help us? Well, it turns out that no matter what your shape of your distribution is, we can actually quantify the proportion of values that are going to be within 2 standard deviations or within 3 standard deviations. What do I mean? So on the next page, I'm going to quantify this more. If you take your mean plus or minus 2 standard deviations, you can be guaranteed, no matter what your distribution looks like, that at least 75% of your data, or your probability in this case, is within that region. And similarly, if I want to do my standard deviation plus or minus, or my mean plus or minus 3 standard deviations, I'm guaranteed that roughly 89% of this area is going to be within that range. So it's actually a nice way, without even knowing what the distribution looks like, if I just give you the mean and the standard deviation, you at least get an eyeball you can eyeball where I know most of the data has to lie. 75% has to lie there, and at least 89% has to lie within that interval. Okay, let's talk about a couple properties that are going to be useful. So here's our definition. Here's standard deviation. First property that's going to be useful is if I actually FOIL this out, which I'm going to do on the next slide, we're going to see a nice shortcut for how we calculate variance. And this will be very helpful when we do some examples. Second property is saying that unlike what you saw with expected value, variance is not linear. So if I take the variance of ax plus b, it is going to actually give me a squared times the variance of x, really because of this squared action that's happening here. And then the last property, which we're not going to prove today, is actually going to show that if you take the variance of a sum of 2 independent random variables, it will be the sum of their variances. Let's use that first property, and I'm actually proving it here for you. So yes, you do have to FOIL this out here, which gets me this, and then combine some things, and at the end of the day, I get expected value of x squared minus the expected value of x quantity squared. Just a reminder, that's the same as mu. All right, let's use this, because most of the time, if you have to calculate variance by hand, this is going to be your go-to formula. It's just going to be a lot faster.